So this is the October-November 2017 9702 multiple choice paper for physics, and this is the 1-2 variety. So we're going to have a look through it. I have had a look through it already, and I thought it was okay. I thought it was quite a reasonable paper. Okay, so the first question says, which pair of units are not the same when expressed in SI base units? So they gave you a list of problems here, sorry, not problems, different units. And straight away, if you look through them, well, you've got meters per second squared and newtons per kilogram. Well, they're the same. Newton seconds and kilogram meters per second, they're also the same. Pascals and newtons per meter squared were the same, but volts per meter squared and newtons per coulomb, well, if you'd studied your electric fields, it should be volts per meter is the same as newtons per coulomb. Next up, they had like a vectors problem, and I've got my little solution here, and it says it gives you the horizontal, and the displacement was 5 kilometers at 37 degrees to the horizontal, but it asks what's the vertical component of the displacement vector. And you had to use sine of 37, the angle there. Excuse me, guys. And I got the answer as 3 kilometers. A specific heat capacity question, and it just asks you what were the base units for the specific heat capacity. And if it's joules per kilogram per degree, well, joules is actually kilograms meters squared s to the minus 2. So the kilogram and the per kilogram cancel out, and you get meters squared s to the minus 2 k to the minus 1. Then you had a uncertainty problem, so you had this equation y equals px over q squared, and then they gave you all the percentage uncertainties. Now, it's actually really, this is such a nice question, because basically you've got, the p is 6%, x is 2%, so that's 8%, and it's divided by q squared. So, well, q is 4, so squared, where you just add the percentages up, which is 8, and add that to the 6 and the 2, and you get a total of 16, so I thought that was D. I've seen this kind of question before. Number 5 was to do with a transmitter, and there's a wave reflected, and they're asking what's the best setting on the time base for the cathode ray oscilloscope. So it says a transmitter emits a pulse of electromagnetic waves towards a reflector. The pulse is reflected and returns. Now that's going to come back to bite you maybe later. If you look at, there's a pulse and then there's its reflection. Now they are 1, 2, 3 squares away, but remember it took time to go there and back. They give you the time just to go from the transmitter to the reflector, which was 6.3 microseconds. So you need to think it's going to go there and back, which is 12.6. And then 12.6 divided by 123 is going to be 4.2 microseconds. There's a hot air balloon problem. So the hot air balloon is moving vertically upwards with a constant speed of 3, and a sandbag is dropped from the balloon. So the sandbag was also going up, so it's going to go up and then back down. Okay, then it says it takes 5 seconds for the sandbag to fall. So what height of the balloon? So what was the height of the balloon when the sandbag was released? So you're looking for S, the displacement. So you're going to use S equals ut plus a half at squared. If you say going down is positive, so the sandbag was minus 3 up, okay? So you say S equals ut plus a half at squared, minus 3 times 5, plus a half times 9.81 times 5 squared, and you get 107.6, which is 108, which is here. There was a velocity time graph, and initially it seems a bit confusing because there's no values given to you, but it just says that the train's acceleration doubles, okay, but the deceleration remains the same. Now, if it's going from one station to another, the total area under the graph should be the same. So the gradient to begin with will increase, okay? In fact, the gradient will double. But what you need to do is, you needed to look at the section where the train was going at a constant velocity. And if you looked at that part there, You just need to make sure that the total area underneath the graph was the same. And I think, what did I get for this? So this was number 7. Yeah, check the area under the graph. I think it's D. Number 8, I've seen before. A stone's released from rest, but it's falling through air. So in that case, if it's going through air, it's going to go towards terminal velocity, which I'm sure a lot of people have probably said A, because it's the velocity time graph curve for terminal velocity. But in fact, the answer is going to be D. So like the curve is going to go down to 0, because eventually when you reach terminal velocity, your acceleration is 0. Number 9, a slow vehicle and a fast vehicle travel towards each other in a straight line and collide. Now this I'm not 100% sure, because I've only just seen the paper and I'm trying to go through the answer. It says, which outcome is never possible regardless of the masses of the vehicle? So both vehicles stop, only one vehicle stops. The faster vehicle speeds increase, the slower vehicle speed is increased. I think it's the faster vehicle speed increased. I think, how is it possible? I mean, would that not take up more kinetic energy? So I think the answer is C, but we shall see about that. Well, I'm not sure. Okay, and number 10, you had this pulley system, and then a large mass and a small mass was doing this. And then it gave you like a load of equations, and you had to work out what is the acceleration of the two blocks. So the total acceleration will be big M plus little m times by A. Okay, that's the net force. And then that net force will be equal to big mg minus little mg, because that's being pulled up. Okay, and I think the answer is going to be, what have I got here? G brackets m minus little m over m plus big M, which was B. That's what I think it was anyway. Okay, then we have this thing about the diagram shows a block of copper suspended in water. It says the block experiences an upthrust in the water. Which statement is the basis for an explanation of the upthrust? Well, it's the idea that the pressure of the water increases with the depth, which is D. And then number 12, we've got a cube, and unless I've misread it, it doesn't seem that difficult. Where you've got the cube is kind of like there's a wire or something going through the very center. Okay, and then it's moved now a distance of L over 4. Okay, and then it says, so it's going to like kind of slip around in one direction. And it says, when viewing the shaded face, what is the torque of the couple that will now be needed to keep the cube at rest? So I think that is that number 12. I think that's B, which is WL over 4 in a clockwise direction. So that's what I thought. That's what I think it is. Okay, number 13, you've got the street lamp. This is quite a common question, where you've got a metal rod and a cable and the lamp. Now, the thing's in equilibrium. So if you look at the vector diagrams, you need to look at which of the vector diagrams is the total addition of all those vectors 0. There's only 2 of them that can possibly be. Let me have a look at here. This is 13, so this is D. Yeah, so D goes all the way around. The other solution that you might have chosen was A, however the forces are in the wrong direction, so it's not A, I think it's D. Then we've got number 14, we've got like a kind of like hinge kind of thing with steel beam. It says, what's the force exerted on each of the beam on the hinges at Y? Well, I think it was A, 2.6 times 10 to the 4. Okay, and then why do I know that? Well, the 4 times 10 to the 4 force going down, that's going to equal 2F times sine 50, and then you just solve for F. And I got 2.6 times 10 to the 4, which is A. Okay, this one, now when the students came out of the exam, they were talking about this problem of there's like a glass bulb and a U-tube, it's submerged in water with atmospheric pressure. So there's a lot going on here, but the pressure of the air in the glass bulb, okay, well, if you actually look at the U-tube carefully, you actually notice that the mercury is lower on the side with the water than the air. So that means the air plus the pressure of the mercury is equal to the atmospheric pressure plus the pressure from the water. So if you just move that over to one side, or move the pressure from the mercury to the other side, it's going to be the pressure from the atmosphere plus the pressure from the water minus the pressure from the mercury is going to be equal to the pressure from the air. Number 6 looks very complicated. It's a projectile motion kind of problem, but simply it says, what's the total work done? Well, the total work done is 0. Why? Because you've gone up and down in the same, you've gone up and down if you think about the force of gravity. Okay, so the total displacement is 0. So there's no work done by the gravitational force during the flight. 17, there's a car going up a ramp, and it says, what's the ratio of the gravitational potential energy gained by the car to the work done by the force, F? So there's a force F going up the car. Now, so it's going to be mgh divided by the force, force times displacement, okay? But with this, you can say h equals s sine alpha. Substitute that in and you get mg sine alpha over f, which was d. Number 18, you've got car X is travelling with half the speed of car Y, but car X has twice the mass. So with this, you need to think about, well, it's going to be a half times 2m, okay, v squared over 4, okay? So in fact, I think car X has got half the kinetic energy of Y. During number 19, during a refueling, a petrol car receives 50 litres of fuel in 90 seconds, and then the petrol has 34 megajoules of energy per litre. For an electric car to receive the same amount of energy in the same time from a 230 volt supply, what's the minimum current that you would need? Okay, so what you could do is work out, well, what's the total energy in all that fuel? And in fact, I've got a total energy here. I think it's 1.7 times 10 to the 9 joules. Okay, then power is current times velocity. Power is current times voltage. You've got the voltage here. Okay, well, the power you can work out is the work done over the time taken. Okay, and then eventually you can work out through there and you get the current. I think it's 8.2 times 10 to the 4, which was B, I think. Okay, halfway through now, almost on question 20. Cambridge loves this kind of thing where, okay, it's a bolt, okay, and the bolt's being pulled apart. The end of the bolt, okay, has a diameter of 2d, and the main part of the bolt has a diameter of d. Now, it says, what's the ratio of the stress of Y against the stress of X? Now, it's the same material, so the Young's modulus hasn't changed. Okay, but what is stress? It's force over the area, not the diameter. So the area in section X, where it's 2D, it's twice as big, is actually going to be 4 times bigger. Okay, so if you work through this, you actually find that I think the ratio of the stress in Y over the stress in X is going to be 4 times bigger. And number 21, we've got a rectangular box. What's the maximum load that it can support? Well, this is just Young's modulus. Okay, and then you're going to use FLE, FL over EA. Now, you've just got to be careful because the compression is in millimeters, and then the dimensions of the cube or whatever it is are in centimeters, so you just need to convert to meters. I worked through this on 21. Let me have a look here. And I think it's A, 32 meganewtons. Number 22, okay, you've got a graph with displacement going up and down like this. And it's what's the kinetic energy? Well, a displacement time graph, if you think what is kinetic energy, it's half mv squared. So we're looking where velocity is going to be, or speed is going to be a maximum. Okay, and speed is going to be a maximum where it cuts through 0 on displacement. So like say if you had something like swinging, okay, well in this case it's a sound wave, okay, but every time displacement is 0, velocity is at a maximum. Okay, so I think wherever you're passing through 0 on the displacement, your kinetic energy should be maximum, and I think the only graph that does that is D. Number 24, you've got a cylinder, it's got some water inside, and then the water's draining out. And they give you two distances where loud notes are heard. So when the water's higher up, it's just going to be an antinode and a node. And then when the water's drained out, it's going to be a node, antinode. Sorry, it's going to be an antinode, node, antinode, node. So wherever the sound wave hits the top of the water is a node. Okay, so with this information you can work out the distance between, let me see here, the two nodes, which is equivalent of half a wavelength, and you get a whole wavelength is 1.32 meters. You're given the frequency, you're given the speed of sound, and then just use V divided by the wavelength will give you the frequency, and I got 256. Okay. Next up, we've got a train, so some Doppler effect. So a train is moving in a straight line along a railway track, and then its whistle is continuously emitting a frequency of F. A woman stands on the track, on the side of the track. She can hear a sound that's 0.85 of F. Now straight away, if the frequency is less, we know that the train is moving away from her. Okay, then we're just going to use the equation, and the equation's in the actual front of the paper. I'm just going to look at my notes again here. So F0 equals FSV over V plus minus Vs. Well, we're going to have to use V plus Vs because we know the train's moving away. And you work through it and you get 51 meters per second, and the train's moving away. 26, orange light in a vacuum has a wavelength of 600 nanometers. What's the frequency? Well, this is just V equals F times lambda, and you get 5 times 10 to the 14. Next up, another one, it's quite a nice question as well. A stationary sound has a series of nodes. Between the first and the sixth node is 30 centimeters. So just remember that's the first node. So between the nodes is 1, 2, 3, 4, 5 half wavelengths. Okay, so you've got 2.5 wavelengths from end to end, which is 30 centimeters. So therefore each wavelength is worth 12 centimeters, which is D. 28, lovely question, which shows diffraction in waters to see. I mean, you've got a gap, the water spreads out. 29 was a bit annoying. It says a hill standing between a radio transmitter and a house is shown. And you just gotta, it's almost a test of English rather than a test of science, because, okay, the radio transmitter is hidden behind the hill, okay, and the radio waves have got a larger wavelength, so they're going to diffract around the hill, whereas the light waves won't diffract as much. And you just got to read through, and there's lots of different options, and I think, what did I say, 29 is C, I think. 30, and then an experiment to demonstrate double slits interference using light. The distance on the slits to keep the screen is doubled and the slit screen is halved. So you're going to use lambda equals AX over D and rearrange for X, get D lambda over A. D is doubled, A is halved, okay, so that gives you a factor of 4 increase, which I think is D. 3/4 of the way through the paper. Then we've got a nice question to do with electric field strength. We've got two plates. What happens as D separates, or the electric field is inversely proportional to the distance of the plates. So I think you're going to get an answer of A, where the E and the electric field strength and the distance of between the plates is inversely proportional. Number 32. This is a little bit of a tricky question. So you've got a uniform electric field, and the electron moves from X to Y. Now you need to think, like, how far forwards does it move through the field? You're told the distance between X and Y is 4 centimeters, but the angle it makes with the direction of the field is 60 degrees. And if you work through it, that means it only goes 2 centimeters forwards into the field. You're told the field strength, and then you use E equals F over Q, work done equals force times displacement, okay, and I got 3.2 times 10 to the 19 joules of energy needed. Divide that by the charge of an electron and you get 2 electron volts. Now if you look here, you've got 2 eV plus or minus. Well, Okay, if it's going in the direction of the field, remember an electron is negatively charged, so it'll actually slow down. So it's actually going to lose 2 electron volts. So I think the answer is actually B. 33. Again, very, very similar to a previous question. You've got a diameter of D and 2D. So again, they're going back to this trick with the area. So it's to do with the average drift velocity of the free electrons in P and Q. And I think that the ratio is 4 again, which I said was D. Okay. Next up, we've got a circuit, 3 resistors. It says there's no internal resistance, so therefore the power out from the cell must be equal to the power lost in R1, R2 and R3 by conservation of energy. Number 35, we've got a metallic conductor, so it's going to be ohmic, it's going to obey Ohm's law. Which of the graphs will give the gradient, will the resistance give the gradient of the graph? Well, V equals IR, so V must be Y, and then I must be X. So the only one that has that is A, where you've got V on the Y-axis and I on the X-axis. 36, a mobile phone battery. It has got an internal resistance of 200 milliohms. What's the terminal PD of the battery when it supplies 500 milliamps of current? Well, you need to work out what's the lost volts. So the lost volts is 0.5 times 0.2, which is going to give you 0.1. And then 0.1 volts subtracted from 5 volts is 4.9 volts, I think, which is B. And is that what I said? Let's have a look. Yeah, that's what I said. Then 37, this is a little bit of a tricky question. You don't often see them mixing circuits like DC circuits with internal resistance, so it's kind of got a bit of a mix of both, which is very creative. It's interesting, an interesting problem. Now we're told the battery itself is 12 volts, but there is an internal resistance, so you need to subtract that internal resistance to find out what's really the voltage being supplied, and I think it's actually only 10 volts that's being supplied. You've got these 2 resistors at the bottom here, R and R, so we know across the total of these resistors is 10 volts. And then I almost tricked myself here because I thought, well, the voltage is split. But actually there's another, this S resistor is supplying an extra 0.5 amps to the final resistor R. So that's going to make things a little bit interesting. So through the first resistor there's only 1 amp. Through the second resistor there's 1.5 amps going through. And then I came up with an equation, 10 equals IR, so 10 equals 1 times R plus 1.5 times R, and I need to solve for R, and I got 4 ohms, which is B. Tricky question, okay? The next one's quite nice though, a potential divider. It's got 12 volts, 300 ohms and 100 ohms, and the 100 ohms is variable from 0 to 100. So if it's 0, the potential difference across there is obviously going to be 0. So what's the range? So when I have 100 here and 300 at the top, so I'm going to do 12 divided by 400 times 100, and I get an answer of 3, which is going to give me A. The last 2 problems, which are nuclear problems. So 39, very nice question, just a decay chain, which is something you might even have seen at GCSE. Neptunium 23793 undergoes 3 alpha decays and 1 beta. So the alpha decay is going to take off 12 nucleons, and you're also going to take off 6 from the proton number. But we've got a beta minus decay, so you're going to add 1 to the proton number. And I think it's radium. I think it's 22588. I think that's what I worked it out as. And very nicely, just to finish off, what's the up-down combination for a neutron? Now, please guys, beautiful question. No one should be getting this one wrong. Up, down, down, and then that's it. We're done. Okay. I thought it was generally quite a nice paper. I didn't think it was that tricky. I didn't think it was particularly easy, but just overall a pretty nice fair question. Sorry, pretty nice set of problems and questions. Okay, bye for now.